So in this video I'll explain how to bias a bipolar NPN transistor using 4 resistor biasing. So let's start with what we know, and in this design let's say that VDD is equal to 10 volt and the collector current is equal to 1 milliamp. So the first step is actually to determine the collector voltage, the emitter voltage and the base voltage. Now let's start with the collector voltage. Now that depends on the design. Now for example, if the circuit would be a common emitter amplifier, the collector would be the output, and very often the collector voltage would be taken to be equal to half the supply voltage for a maximum output voltage swing. So in this case VC could be equal to 5 volt. Now the emitter voltage. Now if the emitter voltage is chosen to be very low or even zero, the emitter resistor will not play a significant role in the biasing. And so the biasing will be very dependent on the transistor, which is a bad thing, as beta, the forward current gain, can vary a lot. If it's high, let's say in this case 3 to 4 volts, then the transistor will be close to saturation, which limits the voltage swing at the input and at the output. Now remember that saturation in an NPN transistor occurs when the base to emitter voltage is larger than 0 and the base to collector voltage is larger than 0. Now a good design value here in this case would be to take an emitter voltage equal to 1 volt. Now the base voltage depends on the emitter voltage, and it's equal to 0.7 volt base to emitter voltage drop plus the emitter voltage, so in this case 1.7 volt. The second step is to calculate RC, RE, R1 and R2. Let's start with RC, the collector resistance. Now the collector resistance is calculated by dividing the voltage drop across that resistor with the current flowing through that resistor. Now in this case RC would be equal to 5 volt, which is VDD minus the collector voltage, which is 5 volt, so yielding 5 volt dividing by the collector current, which is 1 milliamp, yielding 5 kilo ohm. The emitter resistance would be calculated in the same way, meaning 1 volt divided by the emitter current. Now the emitter current is composed by the collector current plus the base current. And that's a problem. It's a problem because the base current is actually not well known. It's not well known because beta, the forward current gain, is not well known. So that value can vary a lot. So let's say in this case we take beta equal to 100. It's an approximation, you never know for sure. Now in this case the emitter resistance would be equal to 1 volt divided by 1.01 milliamp, which yields 990 ohm. So let's calculate now R1 and R2. The current flowing through R1 and R2 is the designer's choice again. Now if that current is too low, then the biasing will be affected by the transistor parameters, for example by the varying forward current gain beta. And if that current is too high, it will cause an increased power consumption. So a design rule of thumb is actually to take the current flowing through R1 equal to 10 times the base current, and the current flowing through R2 equal to 9 times the base current. So that gives you 10 times the base current. This current would be 9 times the base current, and that's actually respecting Kirchhoff's law by taking into account the base current that flows into the base. Now in this case 10 times the base current is equal to 100 microamp, and 9 times the base current is equal to 90 microamp. So this gives you the following values for R1 and R2. So R1 is equal to 10 volt minus the base voltage 1.7 volt divided by 100 microamp, giving you 83 kilo ohm, and R2 would be equal to 1.7 volt, which is the base voltage, divided by 90 microamp, giving you approximately 19 kilo ohm.